Hello once again, and thank you for joining us. This is the Space Nuts podcast, episode 261. I'm your host, Andrew Dunkley, and joining me, as always, is Professor Fred Watson, astronomer at large. Hello, Fred.
Hi, Andrew. How are you doing today?
I am quite well, and I'm very excited. I have news.
Oh, you got
some
news?
Really fabulous news.
Ooh.
I have. Space Nuts is going to be syndicated on the Community Radio Network Australia-wide. Possibly as soon as August, but most likely September. We will be doing a shorter version of the program, but it will be basically available to over 400 radio stations around Australia. So I'm really excited about that. You become more famous, I become more adequate, and we are going to be available to a whole new audience. So
That's very nice.
It's really fabulous.
Yeah.
And the way this network system operates is we'll be given a time slot, and we'll be broadcast on that time slot every week, and that will be available live to the various radio stations, or they can download the recorded version of the program and put it in wherever they like. So we're really thrilled, and it's just one more giant leap for Space Nuts. So it's fantastic news for us.
Yeah, maybe we should.
We don't get.
Maybe we should.
Get paid.
No, we don't. Maybe we should lift our game, Andrew. That's put a bit of effort.
I'm thinking that is a necessity. Yes, but I can't wait. So I'll let you know when that's all on board. On this week's episode, we're going to be talking about an ancient star explosion that is seemingly more powerful than any supernova we've ever seen. This is one cataclysmically massive explosion by the sound of things. And yes, it happened a long time ago, so don't panic. And the story I'm most excited about this week, Fred, is methane plumes that have been detected from Saturn's moon Enceladus. And the headline on the story, which I thought of before I read the headline on the story, was, could this mean life? Well, it is one of the telltale signs, but could be other things as well, but we'll talk about that. And we're going to focus our questions on the UK, because the UK, England specifically, not having a good time of it after the European Cup. Whoops, shouldn't mention that. But James wants to know about some of the fundamental forces and whether or not dark energy should be added to the list. And Duncan is talking about all sorts of bodies in space, but focusing on the Oort cloud and things like that. So we'll answer those questions a little later on. But first of all, Fred, let's talk about this mega explosion that has made the news. And it sounds like it happened a long time ago, but it was one of the probably bigger than a supernova. That's a mighty Big Bang. And was it the Big Bang? No.
No, it wasn't the Big Bang. What do you call a supernova? I mean, a super duper nova? That'd be a good name. But,
that's much too exciting for astronomy.
Well, they're calling it a hypernova, which is...
I like that.
Yeah, I like that too. I like that, hypernova. Maybe 10 times more powerful than a supernova. Remember, supernova... there are several different types of them, actually, but they usually accompany the end of a star because what happens is the star is blasted to pieces. The nucleus itself often collapses, and depending on the mass, it can collapse into a neutron star or maybe a black hole. However, there are chemical elements that we see in the universe that have been thought to have their origin has not been certain. Let me put it that way. So remember, the universe kicked off with just hydrogen and helium, and actually tiny traces of a handful of other light elements as well. That they were created in the Big Bang, and then the hydrogen collected together, formed stars. The stars basically are nuclear furnaces. Their high temperature interiors forged new elements inside. So you get things like oxygen and carbon and stuff like that. And actually helium is also formed, even though there was helium in the original cloud of gas. So what we see is stars producing elements. And then there are certain elements that can't actually be produced inside normal stars, and they include things like lead and gold, the heavier elements, and they have to have much higher temperatures and much more extreme processes to form them. And in particular, gold has been a bit of a puzzle. And in the recent years, when we've seen evidence of neutron stars colliding because we can see their gravitational wave signature, that is one possibility for the formation of gold. But there is another one, and that is one of these hypernovae, something that is even more powerful than a supernova, presumably because it comes about with its progenitor star, the star that is essentially turning into a hypernova, is more massive than the early ones, maybe 25 times the mass of the sun, right, compared with a supernova, which would probably be smaller than that. So that's the backstory, Andrew. So people have gone off looking for evidence of not just gold, but gold in unusual proportions with other elements. One of them is zinc, in fact. So what they've found now is evidence of that having happened in the early universe. So it's not a question here of astronomers seeing the explosion. The hypernova itself has not been seen. That went bang a long, long time ago. Clearly, its light has taken it might have taken a long time to get here, but it hasn't been seen. But what has been seen is a nearby star. Nearby, it's 7,500, if I remember rightly, light years away, which has unusual chemical properties. And it's because of those properties that astronomers have figured out that the only way it can get that particular mix of chemicals is by having been formed from the debris of a hypernova. So this star is not the one that has done the deed, but it's carrying a message, if you like, from ancient times, that back in those days, and it might be 13 billion years ago, there was a nearby explosion that seeded the gas cloud from which this star formed with these heavier elements. So
Sorry, go on.
No, please go on.
Just what surprises me is how we can piece this together with such scattered evidence. Like, we know this explosion happened. We didn't see it. There's no record of it except for the telltale evidence that exists in other forms. It's quite extraordinary. It's almost like you have to be a detective.
Oh yeah. It's very forensic. In fact, astronomers that's the way they work. It's just piecing together these little clues and trying to find the body. And in this case, the body is presumably the remnant of the hypernova. So the story starts with a telescope very close to where I used to work at Siding Spring Observatory in northwestern New South Wales. It's run by the ANU. It is called Sky Mapper, and it does what the name tells you. It maps the sky. It's a survey telescope, so it forms images of the sky, but it does it with a lot of different color filters. And those color filters are specially chosen, so they'll show up unusual things. And one of the things they show up is a deficiency of iron in the star. And a deficiency of iron is a telltale signature of a really ancient star. So even though this star is nearby, it's in our own galaxy, it's very, very old. I mentioned 13 billion years old a minute ago, and that's about the figure that these scientists who are doing this work, who are predominantly Australian, I'm delighted to say, that's the figure they put on it. I've got to tell you the name of the star, Andrew, just because it's...
Oh, yes.
It's SMSS.
Please.
SMSSJ 200322254 minus 114203.3. And I missed out a decimal point there before the 0.54. That name, it's a bit of a cheat, really, because the name it's not a name, it's actually its position in the sky. Those are its coordinates, on the celestial sphere, the heavens as we look at them. And this has got, the details of that is that it's I said it was deficient in iron. Basically something they call the iron to hydrogen ratio. It's the amount of iron in it is about 3,000 times less than the sun, and that pushes its origins back to the very earliest history of the universe, when iron was a very rare commodity. It hadn't been formed by many stars. So it's got this low level of iron, but it's got these other things as well, very high levels of the heavier elements, like zinc, uranium, europium, and possibly gold. That's not been, I think that's not been firmly detected yet. These measurements come from follow-up observations that have been made with the telescopes of the European Southern Observatory, the VLT, the very large telescope down there in Chile, which we in Australia have this strategic agreement with, a strategic partnership with, until 2027. So Australian astronomers not only detected this, but followed it up with actually one of the telescopes at Siding Spring, the 2.3 metre telescope, which is also not very far from where I used to work. My office was in the Anglo-Australian telescope, which is about 300 metres away, probably from the 2.3 metre. And they also followed it up with the very large telescope, as I mentioned. So that's the story. What they've got is the first evidence that such a thing as a hypernova might actually have happened, because they've been predicted, they've been thought about, but nobody's found the firm evidence that they existed until now. And so this looks like a big step forward in the research of the way stars form and the way stars die as well.
So it stands to reason that this probably wasn't the only one in the history of the universe, but this is the first time we've found evidence of such a thing happening because of, the basic fallout of it. Is it something that's going to remain in the past in terms of the universe, or could there be future hypernovas?
They're all in the past because we don't think stars of that mass form now. But of course, the fact that it's in the past doesn't hide it from astronomers, because, we've got this facility to look back in time by looking at very distant objects. So there's a really good chance that we might detect one of these things. And it is thought that they are the source of certain types of gamma ray bursts. Gamma ray bursts have been measured for 20, 30 years now, flashes of gamma radiation. And one possible source of them is a hypernova. And it may well be that when people look at the details of these flashes, in particular, what shape they have when you spread them out in time, like is there a big bump at the beginning and something smaller at the end, or something like that? Those are the details that people will be looking at in future future observations of gamma ray bursts that might betray the presence of a hypernova, or the formation of a hypernova. Yeah. Well,
that will be rather exciting if we can pick up on that.
So that's tying up the loose end from another angle. Yeah.
Yes, indeed. It's a good thing that the products of these hypernovas aren't nearby. It'll ruin our economy.
Oh, it would, yeah.
Gold and zinc.
Yes, that's right.
Yeah. The reason these things remain valuable on Earth is because of their rarity. If we could have access to unlimited quantities of this stuff, we'd be in real strife. Plastic might become very, very valuable.
Don't talk to me about plastic.
No. Although I did read today in the news, Fred, that middle of next year, the Australian government is going to outlaw soft plastics. That includes styrofoam used in packing and all the soft plastic bags, and all of that junk is going to be a goner by the middle of next year, which is really good news. It makes, out of all the plastics, we can only recycle about a quarter of it. The rest goes into landfill, which is, a very unfortunate side effect of our ingenuity as human beings, I suppose. You are listening to the Space Nuts podcast. Andrew Dunkley here, Fred Watson there.
Space Nuts. You've been listening to the Space Nuts podcast. Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com. This has been another quality podcast production from Bytes.com.